Okay, let's flip it over and we'll keep on going. More short answer. The difference of squares will always factor into what pattern? If you have a difference of two perfect squares, you're always going to get a binomial, and it'll always factor into the sum and the difference pattern. So the name of it, we'll call it the sum difference pattern. All right, what is the first rule of factoring? It is, of course, you want to find your GCF. It makes things so much easier. That's the greatest common factor. You're looking for something that can be factored out of everything. And what do I call an expression that cannot be factored? That is going to be our prime. And they're out there. We definitely get them. I'm also going to put down our formula for our sum and difference of cubes. So if you want to have the sum and the difference of cubes pattern, we'll go ahead and add that here. That's the one where you have a binomial, meaning two terms, and a trinomial, meaning three terms. You're going to use same, opposite, always positive to know whether this is plus or minus, to know whether this is plus or minus. But the good news is this one is always positive. You're going to find your A and B. So when you have your values, your A, and you're going to have your B, and you're going to have your A and B here, and this is going to be A squared, and this is always going to be B squared, and this is going to be A times B. All right, let's do some review. So we have some mixed review, and what we want to do is look at each one and know if I have a square here, we're going to try to break it into two binomials. If I have a cubed, I'm going to look for a factor or know whether or not I need to try to factor that x out. Or if I'm looking at something like a special pattern with the sum or difference of two perfect cubes. All right, we're going to zip through these. So what I want you to do is do 1, 2, and 3 and check back in and see if you did it right. Pause the video, please. All right, check your answers. How did you do? So when we have, there's a mistake. When we have, this is a 1. Two numbers that multiply together to give me positive 2. So I need positive 2 and then negative 3 as their sum. So when I think about a negative times a negative, I get a positive. Anytime you have a positive sign here, your signs match. If you know that they match, they're either both negative or both positive, and that here is your hint. If your sum is negative, then that has to be negative 2 and negative 1. All right, so here we have that GCF that we need to take out. A 4 and an X can come out of each of these. Here's that GCF. You still need to hang on to it. He needs to stick around. He's a part of the value. Don't get rid of him. But I have X squared. I'm going to split my X's, and then plus 10 minus 10. Here again is another GCF. Make sure he sticks around. He's worth part of the expression. He's got value. We can't just get rid of him. Now, when I look at 6, it might help you to make a factor table. The factors of 6 are 1 and 6 and 2 and 3. Now, at this point, it turns around. I could write 3 and 2 and 6 and 1, but the commutative property tells me I don't have to bother. Two numbers that add to 5 and multiply to 6. There we go. All right, you've got another row. Let's have some conversations first. So we're going to try to find two binomials here. And check out this sign. How do I know that one of these is going to be positive and one of these is going to be negative? So think about that. Let's take a look at 17. I'm looking at a GCF here, so I know I'm definitely going to be factoring that out. Same thing here. GCF, how many X's can I pull out, and what does that leave me with? All right, you go back and finish these and come back and check your work. All right, so let's check it out. I know that this is negative, so I know that I have one positive, one negative, and then what I want you to think about is what I'm looking for then, because I know my signs don't match, I'm looking for two values with a difference of 2. So once I find these, how do I decide which one goes in the plus and which one goes in the minus? I look at which sign won the battle. So I have more negatives than I do positives, so my greater absolute value goes in that slot. All right, I factored out of 3, and I came up with this new trinomial. So when I think about the factors of 10, I've got 1 and 10 and 2 and 5. My signs match. So that's how I know that they're both negative, because I have a negative sum, even though I have a positive product. So I can pull out 3 x's from each of these terms, leaving me with x squared plus 1. So now, of course, I've got a prime because I've got the sum of squares, which is prime. All right, let's keep going. I see an x I can pull out of each of these. So I get x squared minus 12x plus 27. Oops, what the heck? 27. So now I'm going to think about my factors of 27, 1 and 27, and I've got 3 and 9. That's how I'm going to get x stays out there. I know both my signs match, and they have to be negative. So x minus 3 and x minus 9 sounds like a good combination. All right, here I have a quadratic trinomial, 3 terms. I'm looking at 100 as factors, 1 and 100, 2 and 50, and 4 and 25. How about 5 and 20? And I think about 6, no, 7, no, 8, no, 9, no, 10, and 10. So here's an example of all the factors of 100. I know that my signs are negative, so when I split my x's, I know that one of these signs is positive, one is negative, because how I got this negative is by having a positive times a negative. I know that I'm looking for a difference of 15 because the signs don't match. I know I have more negatives than positives, so that's how I know which values go where. All right, here we have a sum of 2 perfect cubes. So I'm going to go use this pattern from earlier, and we'll go ahead and say A has a value of 10x because that's the cube root of 1000x cubed, and B has a value of 3 as the cube root of 27. I'm going to end up with a binomial and a trinomial pair. My pair is going to have the same sign because of soap, the opposite sign, and always positive. So I've got 10x and 3 for my A and B, 100x squared and 9, and then 30x for my A times B. All right, take a look at 22. We're going to pull out this GCS first. So if I pull out a -1, I get x squared plus 3x minus 18. This negative changes all of those signs, so I want to make sure that I do that first off. Let's think about my factors of 18. 1 and 18, and 2 and 9, and 3 and 6. Not 4, not 5. When I wrap around the 6, so I'm good. So when I try to break that number down, I know I'm looking at a sum and a difference because this is a negative value. The only way to get a negative product is if I'm multiplying it by 2 factors that do not have the same sign. Now that I know that I pull this negative out, when I'm finding 2 numbers that have a difference of 3, here we go, 6 and 3, and guess what? My 6's are positive, my 3's are going to be negative because I have more positives than negatives. All right, again, I'm going to pull out a negative and an x. So if I pull out a negative and an x, I end up with x squared minus 25. Aha, difference of 2 perfect squares. So negative x hangs out. He matters. We hold on to him. I split my x's. This means it goes into a positive and a negative pattern, and 25 is one of my best friends because he's a perfect square. All right, So here we're talking about just looking for the GCF. An 8 can come out of both 8 and 24, one X and one Z. So if I take an 8 out, one X and one Z, what I have left is 3 when I divide 8 out of 24, one X left, no Z's, plus 8 comes out of 8 one time, X comes out of X one time, Y is left over, Z cancels out. We want to make sure we got all the factors by having no common factors left. All right. So we're going to move into this last part, and I know what's coming. I ask you here, look closely at 25, 26, 27, and describe the different kinds of special pattern when we're factoring. So here's what we're getting at here. When I look at each of these values, I see a quadratic, and I see a trinomial, and I'm looking, and I see my best friends. There's 25, 64, and 49. I can see these perfect squares, but it doesn't fit either of my patterns. So we didn't get to talk about this one yet, but my goodness, when I split each of these X's and I look at my perfect square, I'm tempted to just rock on and just keep going with, and by the way, I forgot my 2 here. But what I want to show you is because of these signs, I know I'm looking at what we call a square double square pattern. So I know that 5x is my product of my outer and inner terms. So that's how I get this double. This x, this 10x is my double of what happens from my outer and inner term. So this is what we call a perfect square trinomial binomial because my factors are identical. I can't do that with my sum difference pattern. I can't do that with my sum difference pattern because they're not identical factors. One's positive, one's negative. But here, I know that this was -8 and -8 because -8x and -8x add together to give me -16x. So I can rewrite these as a perfect square. This 4 is a perfect square, so we split into 2x. This sign is positive, so I know that these are both positive, and I can rewrite this as a shortcut using exponents. That's that special pattern that we found. Whenever I have a square, double, square, that's going to factor into some binomial term squared. All right, good job.